Let's pull that up and dive right in. Testing. This post explores a unit and integration testing in no standard executables. We will use Rust's support for custom test frameworks to execute test functions inside our kernel. To report the results out of QEMU, we will use different features of QEMU and the boot image tool. All right, this post replaces the now deprecated unit testing and integration tests posts. It assumes that you have followed a minimal Rust kernel post. Mainly, it requires that you have a cargo config.toml file that sets default target and defines a runner executable, and we do. All right, so we have this boot image runner. Now, somebody in one of my YouTube comments suggested something called cargo x test. So let's take a quick look at cargo x test and see what that does. Crates.io. Cargo X test. Nope. Maybe I'm thinking of something else. That's an XML testing line. Okay, so maybe I misremembered what the YouTube comment said. Cargo post build script. There's cargo post. I thought it was X test, but okay. Obviously, I'm not prepared. So this would take the place of this boot image runner, possibly. But this seems to be built into cargo already. So I think we'll stick with that rather than fiddling around. All right, testing in Rust. Rust has a built-in test framework that is capable of running unit tests without the need to set anything up. Just create a function that checks some results through assertions and add the hashtag test attribute to the function header. Then cargo test will automatically find and execute all test functions of your crate. Unfortunately, it's a bit more complicated for no standard applications, such as our kernel. The problem is that Rust's test framework implicitly uses the built-in test library, which depends on the standard library. This means we can't use the default test framework for our no standard kernel. We can see this when we try to run cargo test in our project. Oh yeah, let's get rid of that panic message. Right, so it's the same error. Can't find crate for test. All right. Since the test crate depends on the standard library, it's not available for our bare metal target. While porting the test crate to a no standard context is possible, it's highly unstable and requires some hacks, such as redefining the panic macro. Fortunately, Rust supports replacing the default test framework through the unstable custom test frameworks feature. This feature requires no external libraries and thus also works in no standard environment. It works by collecting all functions annotated with a test case attribute and then invoking a user-specified runner function with a list of tests as an argument. Thus, it gives the implementation maximal control over the test process. The disadvantage compared to the default test framework is that many advanced features, such as should panic tests, are not available. Instead, it is up to the implementation to provide such features itself if needed. This is ideal for us since we have a very special execution environment where the default implementations of such advanced features probably wouldn't work anyway. For example, the should panic attribute relies on stack unwinding to catch the panics, which we disabled in our kernel. To implement a custom test framework for our kernel, we add the following to our main. Okay. I guess it doesn't matter where it goes. We can just put it down here. What am I doing? Test runner is create test runner. And then in our test build, we have test runner. Oops, like this. It's a list of dynamic, it's a list of function pointers. Okay. And we just say for test in tests, test. Like that. Doesn't like that. Do I have to add something to my cargo toml? Custom test frameworks. Attribute not is permitted in this context. What does that mean? No, it's saying, are you sure you want that with a bang? Maybe the bang thing has to be at the top? Okay. I wonder if this needs to be up at the top. Ah, yeah, okay, so that was it. It has to be the first thing in the list of things. You can't just stick it in the middle somewhere. That makes sense. Our runner just prints a short debug message and then calls each test function in the list. The argument type is a slice of trait object references of the function trait. It's basically a list of references to types that can be called like a function. Since the function is useless for non-test runs, we use the config test attribute to include it only for tests. By the function, I think they just mean the test runner function, not the functions that were being passed in. When we run cargo test now, we see that it succeeds. Well, I mean, it sort of succeeds. It doesn't exit. However, we still see our hello world inside instead of the message from our test runner. Yeah. The reason is that our start function is still used as an entry point. The custom test frameworks feature generates a main function that calls test runner, but this function is ignored because we use the no main attribute and provide our own entry point. Note there's currently a bug in cargo that leads to duplicate lang items. It occurs when you have set panic equals abort for profile in your cargo toml. Oh yeah, we removed that before. Okay. All right, so the custom test framework is still calling is being ignored. The test runner is being ignored. So to fix this, we first need to change the name of the generated function to something different than main through the re-export test harness main attribute. Then we can call the renamed function from our start function. Okay. So this is another one of these hash bangs. Re-export test harness main equals test main. And then in our start function, we currently have hello world. And then if we're doing tests, then we want to call test main. We set the name of the test framework entry function to test main and call it from our start entry point. We use conditional compilation to add the call to test main only in test contexts because the function is not generated on a normal run. When we now execute cargo test, we see the running 0 tests message from our test runner on the screen. We're now ready to create our first test function. Okay. Hello world, running 0 tests. Okay, so I think we're here, right? So let's create a trivial assertion. Assert equals 1 println. Okay. So it looks like we're writing the whole test output. Normally we get this output as part of the test run, but it looks like, with the name of the function we're testing and then the OK message. But here we have to do it ourselves. Reveal assertion OK. So it asserted that 1 equals 1. Very good. Quit. All right. When we run cargo test now, we see the following output. That's true. The tests slice passed to our test runner now contains a reference to the trivial assertion function. From the trivial assertion OK output on the screen, we see that the test was called and that it succeeded. After executing the tests, our test runner returns the test main function, which in turn returns to our start entry point function. At the end of start, we enter an endless loop because the entry point function is not allowed to return. This is a problem because we want the cargo test to exit after running all the tests. This is true. Exiting QEMU. Right now, we have an endless loop at the end of our start function and need to close the QEMU manually on each execution of cargo tests. This is unfortunate because we also want to run cargo tests in scripts without user interaction. The clean solution to this would be to implement a proper way to shut down our operating system. Unfortunately, this is relatively complex because it requires implementing support for either APM or ACPI power management standard. Luckily, there is an escape hatch. QEMU supports a special ISA debug exit device, which provides an easy way to exit QEMU from the guest system. To enable it, we need to pass a device argument to QEMU. We can do so by adding a package metadata boot image test args configuration key in our cargo.toml. Okay, package, metadata, boot image, test args is device, ISA debug exit, comma, IO base equals OXF4, IO size is OX04. Page metadata, so this is just for the test args, okay. The boot image runner appends the test args to the default QEMU command for all test executables. For a normal cargo run, the arguments are ignored. Together with the device name ISA debug exit, we pass the two parameters IO base and IO size that specify the IO port through which the device can be reached from our kernel. Okay, so it's saying the port is at F4, maybe at the address F4, I'm guessing, and the IO size is 4, so maybe that means 4 bytes. I/O ports. There are two different approaches for communicating between the CPU and the peripheral hardware on x86, memory mapped I/O and port mapped I/O. We already use memory mapped I/O for accessing the VGA text buffer through the memory address B8000. This address is not mapped to RAM but to some memory on the VGA device. In contrast, port mapped I/O uses a separate I/O bus for communication. Each connected peripheral has one or more port numbers. To communicate with such an I/O port, there are special CPU instructions called in and out, which take a port number and a data byte. There are also variations of these commands that allow sending a U16 or U32. The ISA debug exit devices use port mapped I/O. I/O base parameter specifies on which port address the device should live. F4 is generally unused port on the x86 I/O bus. IO size specifies the port size. 4 means 4 bytes. Okay. Using the exit device. The functionality of the ISA debug exit device is very simple. When a value is written to the I/O port specified by I/O base, it causes QEMU to exit with exit status, value shifted up by 1 or 1. Okay. So when we write 0 to the port QEMU, 0 to the port, QEMU will exit with exit status 0, shift up by 1, or 1 equals 1. And when we write 1 to the port, it will exit with exit status 3. That makes sense. It makes sense. The calculations here make sense. I'm not sure why it shifts the exit status up by 1 and then sets the lowest bit. There must be some docs on that. Instead of manually invoking the in and out assembly instructions, we use the abstractions provided by the x86-64 crate. To add a dependency on that crate, we add it to the dependency sections of our cargo toml. x86-64 equals 0.14.2. There we go. Now we can use the port type provided by the crate to create an exit QEMU function. Okay, so let's go over here to main again. And we're going to create a new, this seems like it should go in a separate file, but let's do this here. derive, debug, clone, copy, partial EQ, EQ, rep per U32. So this must be the 4-byte port value. Right, pub enum QEMU exit code. Success is equal to x10. Okay. And failed is equal to OX11. So 2 and 3 are success and failure. And then we have a function, pub fun exit QEMU. Right, use x86. 64. I don't know why it's hard for me to type numbers. Instructions. Port. Unsafe. Let mute port equals port new at OXF4. Port write exit code as U32. Okay, so we're writing the port directly. So this must mean the this is already shifted up by 1. So we don't have to do that ourselves. This function creates a new port at F4, which is the IO base of the ISA debug exit device. Then it writes the past exit code to the port. We use U32 because we specify the IO size of the ISA debug exit device is 4 bytes. Both operations are unsafe because writing to an IO port can generally result in arbitrary behavior. For specifying the exit status, we create a QEMU exit code enum. The idea is to exit with the success exit code if all tests succeeded, and with the failure exit code otherwise. The enum is marked as repr U32 to represent each variant by a U32 integer. We use exit code hex 10 for success and hex 11 for failure. Okay, so I misread these, obviously. It's 16 and 17. The actual exit codes do not matter much as long as they don't clash with the default exit codes of QEMU. For example, using exit code 0 for success is not a good idea because it becomes 1 after transformation, which is the default exit code when QEMU failed to run. So we could not differentiate a QEMU error from a successful test run. We can now update our test runner to exit QEMU after all tests ran. So here's our test runner, and now instead of just falling off the bottom of the function, we're going to call exit QEMU exit code success. Should this be a divergent function? It isn't here. I guess I don't know. I guess maybe it should be. All right. So when we run cargo test now, we can see the QEMU immediately closes after executing the test. Okay, let's see if this builds. This does not, because I mistyped this. QEMU. Okay, let's run the test. Blam. Well, I mean, it ran. I saw this the screen flash briefly, and then we got an error test failed. Oh, yeah, that's what we get. The problem is that cargo test interprets the test as failed even though we passed our success exit code. The problem is that cargo test considers all exit codes other than 0 as failure. To work around this, boot image provides a test success exit code configuration key that maps the specified exit code to the exit code 0. All right. So let's go back to our cargo. There's our test args. Test success exit code is equal to 33. I guess we can put in this little comment, OX10, shifted up by 1, or 1. With this configuration, boot image maps our success exit code to exit code 0 so that cargo test correctly recognizes the success case and does not count the test as failed. Okay. So now I should be able to run cargo test. We see the screen briefly show up and then process exited 0. Very nice. Our test runner now automatically closes QEMU correctly and reports the test results out. We still see the QEMU window open for a very short time, but it does not suffice to read the results. It would be nice if we could print the test results to the console instead, so that we can still see them after QEMU exited. To see the test output on the console, we need to send the data from our kernel to the host system somehow. There are various ways to achieve this, for example, by sending the data over a TCP network interface. However, setting up a networking stack is a quite complex task, so we will choose a simpler solution instead. Serial port. A simple way to send the data is to use a serial port, an old interface standard which is no longer found in modern computers. It is easy to program, and QEMU can redirect the bytes sent over serial to the host's standard output or a file. The chips implementing a serial interface are called UARTs, Universal Asynchronous Receiver Transmitter, I think. There are a lot of UART models on x86, but fortunately the only differences between them are some advanced features we don't need. The common UARTs today are all compatible with the 16550 UART, so we will use that model for our testing framework. Whoa, I don't like the way it scrolls. We will use the UART 16550 crate to initialize the UART and send data over the serial port. To add it to our dependencies, UART 16550 is 020. UART 16550 contains a serial port struct that represents the UART registers, but we still need to construct an instance of it ourselves. For that, we create a new serial module with the following content. Oh, okay. So now let's write this out and then go over to main. And we're going to say mod serial here. And we're going to create source serial. Okay, use UART 16550 serial port. We're going to use our spin musex. I'm going to use lazy static. Okay, wrapping the serial port in a mutex. Let mute serial port is unsafe. Serial port new OX3F8. Okay. Serial port in it. Be nice to know where that 3F8 number comes from. Mutex new serial port. Okay. Like with VGA text buffer, we use lazy static and a spin lock to create a static writer instance. By using lazy static, we can ensure that the init method is called exactly once on its first use. Like the ISA debug exit device, the UART is programmed using port I/O. Since the UART is more complex, it uses multiple I/O ports for programming different device registers. The unsafe serial port new function expects the address of the first I/O port of the UART as an argument, from which it can calculate the addresses of all needed ports. We're passing in the port address 3F8, which is the standard port number for the first serial interface. To make the serial port easily usable, we add a serial print and serial println macros. Oh, okay. Lock the serial port, call write format on it with args, and then panic if we fail. Printing to serial fail. Then we're going to say macro export, macro rules, serial print. And this is going to be very similar to the other one, right? Crate. Serial underscore print format args bang arg star. Oh, I forgot the semicolon here. And then we have another macro, which is macro rules serial println. If there's nothing, we're going to print a new line. All right, and if there's a format expr, it can cut a new line to the format. And then otherwise, we have a format followed by any number of args, which converts to create, serial print, bang, concat, bang, format with new line, and all the args. I missed something here. This is for this one. Oh, here.
I don't know what y'all think, but I think that's
there. That's a semicolon, and then we're done with that macro. Very good. The implementation is very similar to the implementation of our print and println macros. Let's see if this even builds. Nope. What did I do wrong here? With the lazy static. Oh, it needs an equal sign, of course. Yeah, and serial 1 doesn't exist. Yuri Burma, thank you for the follow. Very much appreciated. All right, so since the serial port type already implements the format write trait, we don't need to provide our own implementation, right? So we can just write to it, I guess, with write format. Now we can print this to the serial interface instead of the VGA text buffer in our test code. Okay, let's go back to main. And instead of saying println, we'll say serial println. And I guess down here we do serial print and serial println, right? This should build. It does. And then if we run test, oops, it fails. Okay, so let's find out what's going on here. When calling this macro, no rules expected this token. Oh, I must have gotten something wrong. Let's take a look at the other one in VGA buffer so we can compare the two. Right? This has create VGA buffer and it has the same kind of opening. And this has the same kind of arguments here. Oh, but it doesn't use concat. That's the difference, right? I wonder if we should try doing it that way. Let's comment this out and see if we can just get, instead of doing the separate things, we can just say arg tt star goes to create serial print \n and then format args bang arg close star close semicolon. All right. No rules expected this token. Okay. So it must be this, right, that I'm failing on? Let me copy this and put it here, and then change VGA buffer to serial, and delete. Okay, so I must have had a typo there. And let me see what the typo was. Oh, well, it's still We didn't see any output here. That's not good. So what did I have wrong? Oh, it's these curly braces again. Oh, and I forgot the $sign in front of the arg. That's what I was missing. Okay. All right, but the problem is now when we run it. Oh, okay. To see the serial output from QEMU, we need to use the -serial argument to redirect the output to standard out. Okay, so back in our TOML, test args device, and then we're going to add a serial and standard IO arguments. So now if I run test, okay, so we saw the screen flash, but now the output's coming out down here. That's exciting. We're getting closer. When we run cargo test now, we can see the test output directly in the console. However, when the test fails, we still see the output inside QEMU because our panic handler uses println. To simulate this, we can change the assertion of our trivial assert. All right, if I change this to 2 and run the tests, it fails here and doesn't output here. Okay, so are we going to fix that? We can see that the panic message is still printed to the VGA buffer while the other test output is printed to the serial port. The panic message is quite useful, so it would be useful to see it in the console too. Print an error message on panic. To exit QEMU with an error message on a panic, we can use the conditional compilation to use a different panic handler in testing mode. So here in main, where's our... This is the panic handler, right? Oh, I see. So we say CFG not test. If we're not in test config, then we do this one. Otherwise, we'll write a new one for test. And this will do serial println. Error. Info. And then exit QEMU, exit code, fail. And then we loop. We shouldn't have to loop, right? Because we exit directly, but that's fine. For our test panic handler, we use serial println instead of println, and then exit QEMU with a failure exit code. Know that we still need an endless loop after the exit QEMU call because the compiler does not know that the ISA debug exit device causes a program exit. Yeah, but can't we just say that's that, and then that would solve the need for that? I guess not. I guess maybe there's some other issue going on in the compiler. Now QEMU also exits for fail tests and prints a useful error message on the console. Let's try it. Boom. Okay, so now we get the error message coming out here instead of on the QEMU console. Sorry, on the QEMU display. Since we see all test output on the console now, we no longer need a QEMU window that pops up for a short time, so we can hide it completely. Hiding QEMU. Since we report out the complete test results using the ISA debug exit device and the serial port, we don't need the QEMU window anymore. We can hide it by passing the -display none argument to QEMU. So back to the TOML. And I guess now we're going to have multiple lines here, so that's fine. So that'll be the device, and then maybe we can do that one there, and then do this one here. Display, none. I need a comma there, okay? So now if we run, all right, I didn't see it actually pop up. I don't know if you've been seeing it because it pops up very, very briefly. Now QEMU runs completely in the background and no window is opened anymore. This is not only less annoying, but also allows our test framework to run in environments without a graphical user interface, such as CI services or SSH connections. Timeouts. Since cargo tests wait until the test runner exits, a test that never returns can block the test runner forever. That's unfortunate, but not a big problem in practice since it's normally easy to avoid endless loops. In our case, however, endless loops can occur in various situations. The bootloader fails to load our kernel. The BIOS UEFI firmware fails to load the bootloader. CPU enters a loop statement at the end of some of our functions, for example, because QEMU exit device doesn't work properly. The hardware causes a system reset, for example, when a CPU exception is not caught, explained in a future post. Since endless loops can occur in so many situations, the boot image tool sets a timeout of 5 minutes for each test executable by default. If the test does not finish in this time, it's marked as failed and a timed out error is printed to the console. This feature ensures that tests that are stuck in an endless loop don't block cargo tests forever. You can try it yourself by adding a loop statement in the trivial assertion test. When you run cargo tests, you can see the test is marked as timed out after 5 minutes. Timeout duration is configurable through a test timeout key in the cargo toml. If you don't want to wait 5 minutes for the trivial assertion test to timeout, you can temporarily decrease the above value. Well, any test that lasts more than like 5 seconds is too long. So let's do that. Test timeout equals 5 in seconds. All right. Well, maybe there are going to be some future tests that take longer, but let's try this as a timeout test. So let's see if we can run this. Oh, right, I gotta fix the assertion. Duh. There we go. Test timed out. Okay. Yeah, let's leave it at 5 seconds for now, and then we can always increase it later. Our trivial assertion test currently needs to print its own status information using serial println. All right, let's actually get these checked in. Git status, git add source, and cargoes. Git commit. Oh, somebody told me I could use -am. So I don't have to do a separate add stage, and I keep forgetting. Test framework initial config. All right, but we're going to update it now. It looks like we're going to have this automatic instead of each test having to print its own thing. Manually adding these print statements for every test we write is cumbersome, so let's update our test runner to print these messages automatically. To do that, we need to create a new testable trait. And again, we're putting it in main, but this should be its own file. Pub trait testable. Fn run self, and it returns nothing. Do we have to do this, or can we just say this? And we don't get any warnings that this testable trait's not used. Okay. The trick now is to implement this trait for all types T that implement the fn trait. Okay. So impl T testable for T, where T is a function. Okay, run self. Yeah, see this here we don't have arrow unit. Serial print bang dot T core any type name T self serial println. Okay. Yeah, so this is kind of new to me. I'm familiar with any type, but I don't really use it. So this just gets the name of the function, right? We implement the run function by first printing the function name using the anyTypeName function. This function is implemented directly in the compiler and returns a string description of every type. For functions, the type is their name, so this is exactly what we want in this case. The tab character is a tab character, which adds some alignment to the OK messages. After printing the function name, we invoke the test function through self. This only works because we require that self implements the fn trait. After the test function returned, we print OK to indicate the function did not panic. The last step is to update our test runner to use the new testable trait. So here's our test runner. And instead of din function, we're going to say din testable. And then we're going to say test.run. The only two changes are the type of the test arguments, and that we call test.run instead of test. We can now remove the print statements from our trivial assertion test since they're now printed automatically. Cargo test output now looks like this. All right. And it failed. Ooh. Associated type output is not found. Oh, oh. That's why. There it is. So BlogOS : trivial assertion, ... tab, OK. The function name now includes a full path to the function, which is useful when test functions in different modules have the same name. Otherwise, the output looks the same as before, but we no longer need to manually add print statements to our tests. That's good. Oh. Yeah. Let me try this again. I think I messed up last time, right? I want to deny it. And this is just testing the fact that our macros work. So we don't actually need that in main anymore. So let's get rid of this hello world from main. Don't need it. And then the other thing was to add a deny here. No. I can't deny that. Help, you should either use panic or add a call pausing your sleeping thread to loop body. Maybe it's ignore? I forget what it is. Let's find out. There's a way to tell Clippy to ignore it, right? No. Levels. Allow, warn, deny, none. Oh, allow. That's what I need to do. Yeah, okay, now we're clean. Git diff. Right, so we added the testable trait. So now cargo git commit am added testable trait. Cleaned up Clippy. Nice. Yeah, git status. Very nice. Okay. All right. Testing the VGA buffer. Now that we have a working test framework, we can create a few tests for our VGA buffer implementation. First, we create a very simple test to verify that the println works without panicking. So in here, we'll add a test case. Oh, right. I was thinking these would go somewhere else. But okay. Test case. Test println simple. Test println simple output. Okay, the test just prints something to the VGA buffer. If it finishes without panicking, it means that the println invocation did not panic either. And there it is. To ensure that no panic occurs even if many lines are printed and lines are shifted off the screen, we can create another test. for underscore in 0 to 200. Println test println many output. I'm not going to see this output because it's being written to the VGA buffer, right? But we'll be able to run it at least, and it'll exercise all that code. Oh yeah, it took a brief second there to do it, so it's kind of slow. Interesting. We can also create a test function to verify that the printed lines really appear on the screen. Okay. Let's do it that way, since we now have this capability, right? And for IC, in schars, enumerate, that screen char is writer, lock, buffer, chars, buffer, height, -2, because it got shifted up by 1, right? Read. That's going to read just the byte, right? It's an unknown. Assert EQ char from screen char ASCII character C. Why doesn't it know the type here? That's a VGA buffer. Oh, because I forgot to call lock. That's why. Yeah, okay, so now it's a screen character. Okay, good. The function defines a test string, prints it using println, and then iterates over the screen characters of the static writer, which represents the VGA text buffer. Since println prints to the last screen line and then immediately appends a new line, the string should appear on line buffer height -2. By using enumerate, we count the number of iterations in variable I, which we then use for loading the screen character corresponding to C. By comparing ASCII character of the screen character with the C, we ensure that each character of the string really appears in the VGA text buffer. Okay, so we can run this test. Yeah, look at that. It passes. That's good news. As you can imagine, we could create many more tests functions. For example, a function that tests that no panic occurs when printing very long lines and that they're wrapped correctly, or a function for testing that new lines, non-printable characters, and non-Unicode characters are handled correctly. For the rest of this post, however, we will explain how to create integration tests to test the interaction of different components together. Okay, so let's do that. Git commit am adding VGA tests. Okay. The convention for integration tests in Rust is to put them into a tests directory in the project root. Both the default test framework and custom test frameworks will automatically pick up and execute all tests in that directory. All integration tests are their own executables and completely separate from our main.rs. This means that each test needs to define its own entry point function. Let's create an example integration test named basic boot to see how it works in detail. Okay. Let's just grab this. No standard, no main, feature custom test frameworks, test runner, re-export test harness. We have use core panic info. We still have the start function, right? Which is going to be no mangle. We just call test main directly, I guess. And then we can still do the loop, right? And then we have a test runner. Let's get rid of these guys. Oh, we do need panic, but it's just going to do the loop. There's no println. Okay. And we have a test runner, which is unimplemented. like that. All right, so that's the whole thing. Did I miss anything? Test main, panic loop. Okay. Since integration tests are separate executables, we need to provide all the create attributes again. We also need to create a new entry point function start, which calls the test entry point function test main. We don't need any config test attributes because integration test executables are never built in non-test mode. Oh, so we can get rid of this guy. We use the unimplemented macro that always panics as a placeholder for the test runner function and just loop in the panic handler for now. Ideally, we want to implement these functions exactly as we did in our main.rs using the serial println macro and the exit QEMU function. The problem is we don't have access to these functions since tests are built completely separately from our main RS executable. If you run cargo test at this stage, you will get an endless loop because the panic handler loops endlessly. You will need to use Control-C keyboard shortcut for exiting QEMU. Cargo run, test. Okay, so I see it building basic boot, and now we're running, and we got an infinite loop here. Oh, and timed out. Never mind. So we don't need the Control-C because we timed out after 5 seconds. Create a library. To make required functions available for our integration tests, we need to split off a library from our main RS, which can be included by other creates and integration test executables. To do this, we'll create a new source librs file. To make our library work with cargo tests, we'll also need to move the test functions and attributes from main to lib. Okay. So we need these 3, right? And we have this feature. Oh no, config adder. Test no main. But everything else is the same. Okay, we use our panic info. So we're moving these, right? So we're going to move this trait here. We get the... grab this. All right, there's our testable trait, and then we have our test runner. It doesn't need CFG test, I guess. And our test panic handler. And it doesn't need to be annotated with panic handler. But it does have the same exact code. And then we have an entry point for cargo test. So this is just going to be... Oh, I see. So we'll delete, and we'll put that here. We don't need this here, but we do need it here. And we have that. And then I guess this comes out of here. We no longer need that. I don't know. Before I delete it, let's find out. And then we have config test panic handler. And we just call test panic handler. Okay. And just pass that in. Okay. To make our test runner available to executables and integration tests, we don't apply the config test attribute to it and make it public. Oh, we got to make it public. Pub test runner and pub fun test handler. Pub start, and then the panic doesn't have to be pub. Okay. Since our lib.rs is tested independently of our main.rs, we need to add a start entry point and a panic handler when the library is compiled in test mode. By using the config adder crate attribute, we conditionally enable the no main attribute in this case. Oh, I see. So this is saying if test is configured, then we're doing the no main. Here we just say no main directly. Oh, I see. Okay. We also move over the QEMU exit code enum and the exit QEMU menu and make them public. Okay, looks like they were already public. Now executables and integration tests can import these functions from the library and don't need to define their own implementations. To also make println and serial println available, we remove the module declarations too. Like that. I have no idea if this is going to build. Now we update our main RS to use this library. No standard, no main, feature, test runner, re-export, and then we have panic info, and then use BlogOS println. Really, that's all we have to do. Then we have no mangle here for the start function. We still have to do the test main and the loop. We still have this panic, and we still have... Oh, okay. So now here we just call BlogOS test panic handler info. Right. I'm guessing we don't need test runner then? The library is usable like a normal external crate. It's called like our crate, which is BlogOS. Yeah, so BlogOS test runner. Okay, so we don't need test runner here anymore, because we're going to say BlogOS test runner. At this point, cargo run and cargo test should work again. Of course, cargo test still loops endlessly. Okay, does this build? No. What else? Okay. Yep. So cargo test. All right, and then the boot, the basic boot loops endlessly, so it'll die after 5 seconds. So we're getting our tests here. I'm not seeing the other test though. Did I delete it? No, here it is. Trivial assertion. Did I miss it? Huh. Oh no, here it is. Why did I have to build it separately though? Oh. It's doing a standalone build of this, and then it's doing a standalone build of this guy. All right. Let's put the hello world back in our start here. So I can just run cargo run and see if we still see the QEMU window. And it does. Okay, so it still says hello world. So we can still see that and then run cargo test. Let me clean these messages up here, because this should work, right? We shouldn't have this error. This is in basic boot. Oh, right. Okay, basic boot. Yeah, we're still working on that. So completing the integration test. So like our main RS, our test basic boot executable can import types from our new library. This allows us to import the missing components to complete our test. So test basic boot. So this should be BlogOS test runner. And in our panic handler, we should be able to say BlogOS test panic handler info. And our test runner is still unimplemented. Instead of re-implementing the test runner, we use the test runner function from our library by changing test runner to this. We then don't need the test runner stub function in basic boot. Okay. So we can remove it. From our panic handler, we call the BlogOS test panic handler function like we did in our main. Now cargo test exits normally again. Yep, it says running 0 tests. Okay, good. You should see that it builds and runs the tests for our lib RS, main RS, and basic boot RS separately after each other. For the main RS and basic boot integration tests, it reports running 0 tests, since these files don't have any functions annotated with test case. Well, this one does, but we can take it out. Okay. We can now add tests to our basic boot. For example, we can test that println works without panicking, like we did the VGA buffer tests. Nope. Oh, because I have to use it. I missed that line. Use BlogOS println. So it rebuilds it every time. That's interesting. But there it is. Okay. The test might seem a bit useless now since it's almost identical to the one of the VGA buffer tests. However, in the future, the start functions of our main and lib might grow and call various initializations routines before running the test main function, so that the two tests are executed in very different environments. By testing println in basic boot environment without calling any initialization routines in start, we can ensure that println works right after booting. This is important because we rely on it, for example, for printing panic messages. And the power of integration tests is that they're treated as completely separate executables. This gives them complete control over the environment, which makes it possible to test that code interacts correctly with the CPU or hardware devices. Our basic boot test is a very simple example for an integration test. In the future, our kernel will become much more featureful and interact with the hardware in various ways. By adding integration tests, we can ensure that these interactions work and keep working as expected. Some ideas for possible future tests are CPU exceptions, page tables, user space programs. As you can imagine, many more tests are possible. By adding such tests, we can ensure that we don't break them accidentally when we add new features to our kernel or refactor our code. This is especially important when our kernel becomes larger and more complex. Tests that should panic. Okay, so let's get these checked in. Let's do this. Git add. Got integration tests working. The test framework of the standard library supports should panic attribute that allows to construct tests that should fail. This is useful, for example, to verify that a function fails when an invalid argument is passed. Unfortunately, this attribute isn't supported in no standard crates since it requires support from the standard library. While we can't use the should panic attribute in our kernel, we could get similar behavior by creating an integration test that exits with the success error code from the panic handler. Let's start creating such a test with the name should panic. Use BlogOS. I'm going to use QEMU exit code, exit QEMU, and serial println. Serial println. Okay. exit QEMU, QEMU, exit code, success, and then loop. Okay, this test is still incomplete as it doesn't define a start function or any of the custom test runner attributes yet. Let's add in the missing parts. Okay, we export. So we have to define these now. Okay, no mangle. Oh, come on. Loop. And then our test runner. Capital FN. This seems like something that we should be able to make it more generic for. Test in tests, test serial println, test did not panic. Oops. Exit QEMU, QEMU. Exit code failed. Code success. That's it. Instead of reusing the test runner from our librs, the test defines its own test runner function that exits with a failure exit code when the test returns without panicking. If no test function is defined, the runner exits with a success error code. Since the runner always exits after running a single test, it does not make sense to define more than one test case function. Now we can create a test case that should fail. I guess we have to add serial print as well. And here's our test case. Oh. Should panic, should fail, ... assert EQ 0, 1. Okay, the test uses the assert EQ to assert that 0 and 1 are equal. This of course fails, so that our test panics as desired. Note that we need to manually print the function name using serial print here because we don't use the testable trait. When we run the test through cargo test -- test should panic, we can see that it is successful. Because the test panic as expected. When we comment out the assertion and run the test again, we can see that it indeed fails with the test did not panic message. Oh, did I? No test target named should panic. Oh, because I put it in the wrong directory. And I have typos. Let's see if it catches it. Nope. What else? That's it? Okay. Should panic, should fail. Okay. Significant drawback of this approach is that it only works for a single test function. With multiple test case functions, only the first function is executed because the execution cannot continue after the panic handler has been called. I currently don't know of a good way to solve this problem, so let me know if you have an idea. No harness tests. For integration tests that only have a single test function, the test runner isn't really needed. For cases like this, we can disable the test runner completely and run our test directly in the start function. The key to this is disable the harness flag for the test in the cargo toml, which defines whether a test runner is used for an integration test. When it's set to false, Both the default test runner and the custom test runner feature are disabled, so the test is treated like a normal executable. Let's disable the harness flag in our should panic test. So here in test, we say name is should panic and harness is false, like that. Now we can vastly simplify our should panic test by removing the test runner related code. So we just need no standard and no main. We don't need any of that. We still need panic info on our BlogOS stuff. Our test changes to should fail. Our start changes to just should fail. Like that. And then we can have test did not panic here. And then we can call exit QEMU. Right? And I get rid of this whole function. In fact, it looks like we don't even... Oh no, that changed. That doesn't change. Okay. So now it fits on one screen. Oh, test case doesn't exist anymore. And it looks like serial print doesn't... No, it's right there. Oh, because I did test case. Okay. And then should fail, I'm missing a semicolon. Okay. We now call the should fail function directly from our start function and exit with a failure exit code if it returns. When we run cargo test should panic. Now we see that the test behaves exactly as before. Apart from creating should panic tests, disabling the harness attribute can also be useful for complex integration tests. For example, when the individual test functions have side effects and need to be run in a specified order. Adding a should panic test. Okay, I think we're done. Summary. Testing is a very useful technique to ensure that certain components have desired behavior. Even if they cannot show the absence of bugs, they're still a useful tool for finding them and especially for avoiding regressions. This post explained how to set up a test framework on a Rust kernel. We use the custom test frameworks feature of our Rust to implement support for the simple test case attribute in our bare metal environment. By using the ISA debug exit device of QEMU, our test runner can exit QEMU after running the tests and report the test status out. To print error messages to the console instead of the VGA buffer, we created a basic driver for the serial port. All right, so this is done here. So the next thing is going to be we finished bare bones, and then we're going to work on interrupts, and that's going to be the next stream. All right, so git push. Let's push these guys up. Let's take a look here. There's all our test code. And that wraps things up for me.